Professor John B. Burrows, I'd like to welcome you to University of Crete and of course to 10 Days of Ingenium, which is hosted to University of Crete. And I'd like first to ask you, what was the scientific question that inspired you to engage in atmospheric remote sensing?
So my scientific career began when my doctoral father in Cambridge University in England offered me a position to work on reactions which are important to maintaining the ozone layer. And at that time, in the early 1970s, middle 1970s, there was a threat to the ozone which had been recognized, which was created by the generation of long-lived so-called chlorofluorocarbon compounds. Now at the time, this was thought to be a slow process with maybe, by about 1980, we thought maybe 6% loss globally, and the industry was being asked to reduce. But then suddenly, exactly 40 years ago this week, there was a paper published called Loss of Ozone over the Halley Bay Station in Antarctica, and this was actually the discovery of the ozone hole. Now, 12 months before that, my director, Professor Paul Crutzen, asked me to start working on measurement techniques, okay, to move out of the laboratory where I'd been very busy and enjoy myself. He said he'd really like me to work on measurements, and I was doing measurements like here in Crete, on the ground or from the ground, of different kinds. But literally over a cup of coffee, we were talking, and I figured that a technique called differential optical absorption spectroscopy, which had been developed by my line manager, Dieter Perner. So I was talking with him and Paul Crutzen, and I said, I think this technique will work from space, you know, because why not? You know, we look at passive remote sensing, you take the light from the sun, it goes through the atmosphere, it's modified by absorption and emission, and these absorptions and emissions by gases and also at the surface tell us information, sort of fingerprint information about gases and also surface and what's in the ocean. So I said, this should work, and they said, probably you're right, or you might be right. And I said, well, I'll start working on this. And then with the help of my bosses and superiors, that's how it began. And then some years later, after going to many meetings with the European Space Agency, there was an opportunity to create a mission proposal for an instrument on what at the time was known as Polar Platform by ESA. And this had been spun off from the then Star Wars, for those who are old enough to remember that discussion between Europe and America. But this was then a Polar Platform. It was going to be dedicated to research, atmospheric surface research. And I was looking for a name, and I created a team with my colleagues, and we created a proposal. And the name came from my thinking and talking with the group about scanning, imaging, absorption, spectroscopy, and eventually I came up with the name Scanning, Imaging, Absorption Spectrometer for Atmospheric Cartography, which means mapping of the atmosphere. And out of that we got SCIAMACHY, which is of course a Greek word meaning chasing the sky, or kind of has the meaning of doing a difficult task.
Because after all, it's all Greek.
That's right.
So that was the beginning.
That was the beginning. And well, both my good colleagues there, and there were several other good colleagues working with me on the project, Wolfgang Schneider, Geert Murtgat, and people in the institute. But I had the opportunity to lead this adventure, and we submitted a proposal, and you go through very strong peer review and also financial review, technical review. And although our idea was very new at the time and that we hadn't had a previous mission or something, we were not experienced space scientists, we managed to convince the European Space Agency and its review boards, and we were selected for what's called a Phase A study for SCIAMACHY. And at the same time, ESA was so concerned about the ozone hole, which I'm saying in 1985, and that Europe should have a strategic opportunity to have its own measurements. It's very good working with NASA. In particular, they were very helpful and very useful and part of our team. But it's very good to have an independent strategic measurement capability. You don't want to believe the other measurements necessarily, even though I think we have great measurements from NASA and NOAA. But we wanted this strategic capability. And ESA basically agreed, and so we started on a Phase A. And then, as Dieter Perner said to me, now you have to get it done.
So how are data from satellite instruments used to understand climate changes, and what is your observe for 10 years now? Is it getting more worse than it was?
What happened is that, what the objective is to have a measurement system which meets adequately the capability of measuring at the right temporal and spatial resolution. Now, a pioneering instrument like SCIAMACHY, or then we had the luck to have this second instrument, which we originally called SCIAMINI. So at the end of that year, ESA was so interested that they asked for a second call to have a small instrument. They had identified on an existing satellite that was about to be launched, they identified that they had resources, which means mass, power, data rate, budget, and we won that opportunity as well, our team. And what was originally called SCIAMACHY became known as the Global Ozone Monitoring Experiment. So the focus was then on the ozone problem. But SCIAMACHY, which then came onto the polar platform, as I explained, about, the GOME was launched on ERS-2, it's called, the second European research satellite from ESA. That was launched in 1995, okay, and then MVSat came in 2002. Now, on MVSat, for the first time, we employed a kind of new idea, which was to measure in what's called the near-infrared, short-infrared wavelength region. We were measuring carbon dioxide and methane. Okay, now these are the most important man-made climate gases. So we were able to see from that beginning, admittedly then at low resolution, spatial resolution, and only maybe once every few days, we could look at the whole globe and see the increasing amount of CO2 and methane. And you can see the Earth breathing. You can see CO2 going up in spring when the biosphere degrades and some CO2 is released. And you can see it going down between May and September in the Northern Hemisphere. So you have a kind of sinusoidal behavior. And on top of that, you see the increase, which is due to the anthropogenic release of CO2. And similarly, we see increases of methane. And methane is more complicated because actually at the time of our first measurements around 2002, methane was sort of stable. It had gone up, so pre-industrial, it was in these units, which I'll give you, which was 0.7 ppm. It's now over 2 ppm in the surface layer. So that means a double. So since the Industrial Revolution, it's gone up by over a factor of 2, maybe 3 even. And that is coming from the release of methane from cows, so-called enteric fermentation from all of these cow-like animals, from waste out of the soil, from exploiting coal, where you release methane, and from exploiting methane as a fossil fuel energy and having leaks, like in fracking. And there are many sources, so this is coming up, and a lot of these sources have been growing along with population. So at the Industrial Revolution, we had 1 billion people. Going back even further, we had the beginning of the civilization with the settlement at the Neolithic Revolution, shortly after the last ice age. Close to here, the first settlements started. People started living in beginnings of urban areas. We had 4 million people. Go to the Industrial Revolution at 1800, we have 1 billion people. Recently, we've passed 8 billion. And when I was born, I'm quite old now, but when I was born in the 1950s, it was maybe 2 to 3 billion. So we're seeing a massive increase of humans, a massive increase of the use of agriculture to produce food. This also releases nitrous oxide, which is N2O. That's another greenhouse gas. Okay, so mankind is releasing, these are the 3 most important greenhouse gases: CO2, methane, and laughing gas, nitrous oxide. Okay, and
which one is more dangerous?
In this sense, they're not dangerous that you can breathe them, as long as you're breathing enough oxygen and nitrogen. But they're dangerous because they have infrared absorptions. And actually, the so-called global warming potential of N2O and methane is much higher than that of CO2. But we release a lot more CO2, and there's a lot more CO2 in the atmosphere. The CO2 is now over 400 in these ppm units. So I said methane is about 2 ppm. CO2 is about 400 now, a little bit higher, 420, but about 2 ppm per year increase, okay? And that means, although it's less strongly absorbing, there's so much being released that it remains the dominant impact on the increase in temperature at the surface, which is what global climate change is. Methane is then second, and N2O is third.
So, Professor Burrows, can satellite remote sensing be used to predict natural disasters or pollution events?
I'll start with the second. Pollution events, definitely, because there are 3 things that the SCIAMACHY Pathfinder Explorer type mission of ESA was aimed at, and one of which I've said is the ozone problem. That problem, just to recall it, is still a major problem, but the political issues have been put in place with the Montreal Protocol and its amendments from 1987 onwards. So we've stopped basically releasing the problem chlorofluorocarbon compounds and bromine compounds, the halons. So we now have to sit it out, and we'll have an ozone hole for maybe another 50 years, but it should be going away, maybe a little bit less if we're lucky. Urban pollution was already a big problem, and that's smog. And smog, we know, smog is the name for a mixture of smoke and fog. In English, it was actually defined by, this word came up was proposed by a Belgian around about 1900, and we have London smog, which is very acidic because of the burning of coal and the release of sulfuric acid. So or release of sulfur dioxide, which becomes sulfuric acid. So if you breathe that, it's acidic, it's bad for your health, okay? This type of London smog was well known, P supers, and in 1952 killed about 10,000 people in England, and the first Clean Air Act. Now we see smog, and we see the precursors of smog from space, okay? Now, in about 1948, there was a second kind of smog discovered in Los Angeles. This is summer smog, okay? And this produces ozone and aerosol and toxic compounds. So when you breathe these, you're affected by them. And both of these, air pollution is approximately costing about 8 million lives a year in the world. About half of that is outdoor pollution, so about 4 million, and half of it is indoor air pollution. I'm just talking about air pollution, I'm not talking about water pollution, which is in addition.
Or food pollution.
Or food pollution. I'm just talking about air pollution here, that 4 million people from wandering around outside are going to get a year sick and ill and whatnot, and the estimate is about 4 million a year. And from people living in poor housing where you're getting a lot of pollution from cooking or whatever, that's another 4 million. So it's about 8 altogether, okay? And that's surprisingly large.
You have spotted special areas like around the world, like China, for example, or India, or Africa maybe?
Well, let's just take an example on urban pollution. So one of the great things that SCIAMACHY started, or SCIAMACHY and GOME started, was the measurement of nitrogen dioxide. Nitrogen dioxide is a pollutant which is made as a result of combustion, because nitrogen and oxygen form nitric oxide. Nitric oxide then reacts with a bit of ozone that's already there to make nitrogen dioxide, and then there are cycles which make more ozone and aerosols, and then we have smog if we have enough of it. We can see from space nitrogen dioxide. We can also see the hydrocarbon or oxygenated hydrocarbons like formaldehyde, I think called glyoxal and more, and we can see these things from space. So we can see the conditions that are building up. So we can help models. So I work closely here with the University of Crete on the modelling in Professor Maria Knakidou's department. And so we're providing the measurements. They can then compare measurements with models and make predictions. And this is all part of a European effort now being run really by the European Centre for Medium Range Weather Forecasting, which is called CAMS, which is paid also by the European Union. And this is about improving prediction of air quality. Okay? If we go back to China, which is your question, we published a paper early on in 2004 saying from our measurements we're seeing a rapid increase of oxides of nitrogen in China, which did not agree with what local people had been measuring.
They're different.
They were different, okay? And then the question
which is the truth?
Which is the truth? Well, it turned out that ours was the truth, or at least closer to, there's no real truth, but we were much closer to the truth than they were. So either they'd been measuring wrong or reporting wrongly. Who knows? But now they then took it seriously. They even, maybe I shouldn't say this, but they had some suggestions at that time that maybe people should not combust fuel in the mornings when the satellites were coming across to try and avoid being seen. This reminds me of where I grew up, which I grew up in the birthplace of the Industrial Revolution. Many companies, which is close to Liverpool in England, many companies would release pollution at night. And you would wake up in the morning with dirty windows, and so, you know, this is human nature.
It's a disaster, sorry.
But the good thing is when you're measuring it, when you're providing evidence, and you can discuss the evidence, you can validate. Here, close by here, we have measurement stations validating the satellites run by the University of Crete. This is the scientific effort. Our job is to deliver the information, provide the evidence base, and then journalists, politicians have to decide how you deal with this.
Do you believe policymakers take scientific evidence about air pollution seriously?
Well, they do and they don't. I remember President Nixon being quoted with respect to the ozone hole scientists, who were my seniors when I was a young man, asking whether or not they had any dirt on these people. So they didn't. These were just good, normal working scientists. So I think politics is a different game, and scientists aren't very good at it. We should do what we're good at, which is delivering the evidence and making compelling case for saying why these things are happening. For example, pollution, again, doesn't just affect humans. In Europe, the estimates for agriculture are about 8 billion a year. Because when you have ozone, ozone up there is good because it protects us from being, getting cancer, because of skin cancer, okay, in particular, with the UVB. So it's good when it's in the stratosphere where it's supposed to be. Down here, as part of pollution, it's bad. So there's kind of good ozone and bad ozone. Bad ozone, for example, affects leaves. In fact, there's a measurement technique. You can use tea plants to see the number of white spots on a leaf, and that's proportional to the amount of ozone in the air, okay? And ozone's toxic. So what I'm trying to remind you, it's not just the people who are dying, it's also the agriculture. Europe estimates around 8–10 billion a year, euro lost, this type of thing. So we have policymakers in Europe, I think, are taking this seriously. Policymakers around the world have been taking this seriously. The US has been, in the past, the United States has been an excellent leader. They made great and strenuous efforts to deal with the ozone issue, also with releases of sulfur dioxide pollution related.
What happens now?
The current government has an anti-science or anti-climate change science, and they're at this time and since January been firing people who work on these topics, and firing young people first of all, and have a plan to do very much less, or practically, as far as I can see, very little climate and environmental science, and concentrate on things like flying to Mars, which I don't think is as important as cleaning up this planet. I think before we go to Mars, we should have a clean Earth.
So that would be dangerous for your experiment, for the science, for the next years?
Well, the first thing is when people have been working hard and successful and contributing to the science effort internationally, because the American scientists are very internationally orientated, and providing data free for all of us, that data will be maybe lost, and we will therefore be less able to predict change with the loss of these scientists. First of all, for the scientists, it's personally very disappointing and sad, but for the... I experienced some of this in the United Kingdom when Mrs. Thatcher tried to privatise a lot of science, government science. It's not science isn't necessarily, government science isn't necessarily something which fits well to the marketplace in classic economic senses. It's something that has science, government science is delivering something that people maybe don't want to know how bad the air quality is, or that type of thing. So I think the current situation is very disturbing. It's very sad for those scientists who are good scientists who are being fired for no reason other than that the new administration has promised that it's going to do this, and it's going to create a problem because probably something like 40% of the world research on climate is taking place in the USA. Oh. Europe's taking it very seriously still. We have to see what long-term consequences it has.
Professor Burrows, what do you consider the greatest challenge for remote sensing in the next 10 years?
The challenge has been from the very beginning is to create an adequate system in terms of spatial and temporal sampling. In order to see something, you have to sample faster or on a smaller, slightly smaller spatial scale than the event's happening, okay? So if you want to see a car crash, you have to be able to maybe have pictures with maybe a few centimeter resolution, okay? And so it depends on the scale of the problems. What's happening is an evolution. We started with very poor, SCIAMACHY, wonderful though it was, and GOME were low spatial resolution and maybe once every 3 or 6 days, okay? We're now going to have this year a thing called, what I originally called GeoSkia, but is now going to be called Sentinel-4. That's starting in a few weeks. That will do diurnal variations, okay, by measuring from geostationary, and we can then look at the same Europe all the time and scan once half an hour or an hour. So we get the temporal resolution. We will then see the traffic jam pollution mornings and evenings. We will see the emissions from trees, which are proportional to the humidity and temperature, which are producing the fuel along with the oxides of nitrogen to create ozone and smog. So we'll have, that's going to be new and exciting. And unfortunately, although we proposed it first, there's already one over Asia from the South Koreans, and also one as of last year or 18 months ago now, over the USA. So we're going to have a kind of fleet of these things, with the European one called Sentinel-4, which we proposed originally with the name GeoSkia, but it's become a community instrument, and that will be starting, and EUMETSAT, the European Union. So I think one of the big challenges is to get these operational systems working and providing the data, and also a big challenge is to getting the data to the people in the right form. So that's why we need the modelling and the interpretation of the models and providing the information so you get a good warning of smog, and that's going to be easier to do. This morning, you know, we had an earthquake around here, and that's exciting. Unfortunately, seems like nobody's been really hurt, hopefully. But that's a really difficult problem to solve. We can measure earthquake changes, but I think in comparison We know how to do the pollution, the climate change. We need good measurements. We know how to do them. It's purely a question of cost. Some years ago, I wrote a short notice for the European Space Agency, which said if you put a 0.1% tax on oil, gas, coal equivalent, so 0.1% when you tank, when you fill up your tank, you don't notice.
Of course.
But that would be so much money that we could have a fantastic science system for the world, okay? Satellite system. So it's just a question. I think we know how to do it. There are lots of technical challenges. We have the engineers, we have the capability across Europe, including strong efforts here in Crete and in Greece. And we just need to do it. It's just a question of political will, in my opinion. And that's possibly the most difficult thing.
Yeah, I know. I can imagine. Is there satellite traffic? And are you worried about what happens when a satellite is explode in the air, in the space?
Yes, I am, and this is a new problem. So colleagues of ours in Braunschweig in Germany, so friends of mine actually have proposed, proposed the question in 2021, what's happening to this aluminium and all the metal, okay, coming out of satellites. And then some other colleagues of ours at NOAA in Boulder in the US, they measured in the stratosphere the aerosol particles which form there. And this is a natural phenomena, but it's influenced by dust, so metals, metals coming in, dust coming in, or satellite debris coming into the satellite waste, I think we want to call it now, coming into the atmosphere, starts hitting the atmosphere, and there's friction that heats these particles up to maybe 2000 degrees centigrade, that sort of temperature, and they ablate. So they ablate, they boil off the metals. This then comes into the atmosphere and starts clustering and making aerosols. So the question is, what are these aerosols doing? First of all, you can say, are they going to increase the number of aerosols? And then what's going to happen? That could be result in an increase in the total amount of stratospheric aerosol, which is reflecting solar radiation back to Earth. That would be a dimming or cooling effect. Okay, so that would actually make it a little bit cooler, which maybe some people say is good because we're making it hotter anyway, but we already have a lot of experience in it. This is what happens when you have a volcanic eruption. You have a cold or no summer sometimes after a large volcanic eruption into the stratosphere. So we know about this kind of issue. So we have to see, what's the size? We don't know yet. The other unknown is it going to influence loss of ozone, either in the polar vortices where you have the ozone holes, or globally. And we don't know that yet. That's a research problem. So I am concerned about it. And I think that may limit, depending on how much damage to ozone, or how strongly it's influencing the amount of aerosols are influencing the solar radiation being reflected back to space, or possibly even being absorbed from radiation leaving the surface. These are new questions for the science. It's a new problem, but this could well, if the damage was sufficient, or the assessment of damage indicated a major problem, that may limit the number of satellite launches into the low Earth orbit that we can do. So this is a really serious problem that needs to be sorted out.
So this is my last question, and it is about a University of Crete. And what is your impression from University of Crete? I'm
very impressed with the University of Crete. Like my own university in Germany, in Bremen, these are young universities. They're 50 years old, of that order, and I think they've both grown to be leaders in their fields. They've also taking the opportunity to do because they don't have, tradition can have advantages and disadvantages. My own alma mater is Cambridge University, that has a wonderful tradition and extremely successful in science. But new universities can also work on new topics. And I think Crete has been very successful working on traditional, but also working on new topics like, for example, climate change, urban pollution, and the ozone. The ozone game now is really watching to see, we think we know what's going on, to check that it's going to be like that. A few years ago, Some colleagues measured an increase in chlorofluorocarbons from China again, so some people were breaking the law and making them again. So you see things like that. So we need this global observing system, and that's a big enterprise for the whole of science, and I'm glad to say the University of Crete is heavily involved in that. We have a very nice station not very far from here,
Φινοκαλιά,
which makes excellent ground validation measurements, and these measurements are not just validation because they're their own record, and you need it. You need the local record and the global.
Professor Burrows, thank you very much for this conversation.
Well, it's my pleasure.